We have already specified which is going to be the plane wave basis set we are going to use to describe the matrix elements of periodic solids. And the basis set we are considering was the following. The different elements on the basis set, they are identified with this G vector. This G vector is the reciprocal lattice vector, and we are going to have a basis set for each K vector in the Brillouin zone. So this is the plane wave basis set we are going to use. And in this plane wave basis set, the matrix elements, that's what we are going to calculate, of the Kohn-Sham equations are going to be very easy to calculate, as we'll see later. And this is actually one of the advantages of using the plane wave basis set. Okay, if you remember, there are different elements arising, the different matrices arising in order to describe Kohn-Sham equations in the matricial form. One of these matrices was the overlap matrix. But in this case, as the plane waves we are using here, they are orthonormal actually. This overlap matrix is the identity. Okay, this is the different elements of this overlap matrix. As you can see here, as you will be using the reciprocal lattice vectors in order to identify different elements in the plane wave basis set, we're using the same indexes. In this case, the G vector are going to be the indexes that we're going to use in order to describe the elements of the matrices. So different elements of the overlap matrix are going to be identified by the G vectors. And the same way for other matrices that we're going to describe next. And actually, as we do have a matrix, a basis set for each K vector, we are going to have in the same way one matrix for each K vector. So, but in this case, as we have said before, basically the definition of this overlap matrix is given by this one, by the inner product of these two elements in this plane wave basis set, and that's the identity. So that's a very interesting simplification in order to have the Kohn-Sham equations in the matricial form. The overlap matrix is the identity. So the next matrix that we need to specify for the Kohn-Sham equations is the Hamiltonian associated with Kohn-Sham equations, which it includes the kinetic energy and the Kohn-Sham potential energy. So that's what we are going to, the matrix that we're going to describe next, which is the one which is associated to the Hamiltonian. Okay, first we are going to describe the matrices associated with the kinetic energy, which again, the different elements in the matrix are going to identify by the G prime vectors, and we're going to have a matrix corresponding to each K vector in the Brillouin zone. So in doing that, calculating the matrix elements of the kinetic energy is as simple as calculating this one, because in this case the operator is -1/2 the Laplacian. So calculating this one, it's extremely simple. So again, as have in mind, when doing this integration of real space at stand here, we have to do that in the primitive volume. Okay, and doing that, you can see that the result we're getting is this one, which again, as you can see here, that's diagonal in the reciprocal space. That's great, because it simplifies a lot the matricial representation of the kinetic energy. So that's the one corresponding to the kinetic energy. And the next one that we are going to calculate is the one corresponding to the Kohn-Sham potential. And it's important to keep in mind that the Kohn-Sham potential, which actually is going to be a function of the kinetic, of the electronic density, is just local, which basically means that just depends on position vector r. And that's going to be very important in order to calculate different elements in the corresponding to the Kohn-Sham potential energy, which we are going to do it next. Okay, basically, again, calculating different elements corresponding to the matrix of the Kohn-Sham potential. Okay, that's what we have to do is this one. We have to calculate that integration here. We have to calculate this one. But that's very easy to do again because this is local, so we have to calculate that integral here. As the k component we do have for these two vectors are the same, you can see that this disappears from here, and this is the final result we have. This is the final result, the final integral that we have to calculate. And basically what we have here is the Fourier component, the Fourier transform of the constant potential, of this potential. So the matrix element corresponding to the constant potential, the GG prime component, is basically this Fourier transform of this constant potential. So we do have everything in order to have the constant equations considering this plane wave basis set, and the constant equations writing in this plane wave basis set are given by this equation here. Here we have the kinetic energy component. Here we do have the potential energy component. These are the coefficients that we want associated to the expansion of the constant equations in the plane wave basis set. Here is the eigenvalue that we do have. And again, here we have the expansion coefficients of the constant equations in the plane wave basis set. So these are the equations. Of course, we can write this equation here in a more compact way using the matricial form, which is this one. So that would be the matrix for each k vector, of course, corresponding to the Hamiltonian, the kinetic and the potential part included here. Here is again the coefficients of the expansion in the plane wave basis set right in the column form. This is the eigenvalues, and this is again the coefficients right in the column form. So basically what we do have here is the, writing this way, is the eigenvalue and eigenvector problem. So for each k vector, we have this equation here, this matricial equation here. We have to calculate which are the eigenvalues and the eigenvectors. And from that, we are having a number of eigenvalues and eigenvectors corresponding to each k vector. And for different k vector, we are going to have another one. For different k vector, we are having another one. And as k vectors are going to be one close to the other, so finally what we do have is like a band. We have a band here. We have a band representation and in k space. So that's the final results that we are getting. And in order to get that, so basically again, what we have to do is to solve that eigenvalue and eigenvector problem. Of course, we do have some problem here in the sense that the dimensions of the matrix we do have here is infinite, because we do have an infinite number of j vectors in the reciprocal lattice. So how can we solve that? Because this is an important problem in a practical way, because we do know how to solve the eigenvalue and eigenvector problem when the dimensions of the matrix we do have is finite. But how can we deal with infinite matrices? At some point, it's clear that in a practical way, we need to truncate that matrix somehow. How can we do that? Okay. As we have said, the j vectors we do have in this plane wave expansion, which are the reciprocal lattice vectors, and in principle an infinite number of vectors. And of course, they are required in order to represent the wave functions with infinite accuracy, of course. But in practice, and this is important, what's usually done is that the Fourier components, the expansions we do have in this the plane wave expansion series of these constant equations, these components, they decrease with increasing k plus g modulus. So for higher the g, the effectiveness of these coefficients, they decrease, so that the plane wave expansion can be effectively truncated at finite number of terms. So usually we consider finite number terms in the expansion. And usually the usual way of doing that is the following. Usually it's limited to all waves with a kinetic energy lower than some energy cutoff. So in order to do the numerical calculation, you have to specify which is the energy cutoff you want to include in order to consider the finite matrices. Of course, the higher this energy cutoff is you consider, the accuracy is going to be better. But at some point, it will be like a compromise between the accuracy that you required and the computational resources that you might have, because of course, as bigger the matrix is getting, the computational resources that you need in order to calculate the eigenvalue and eigenvector problem is going to be higher. So it's going to be like a compromise for that. You have to take into account what's the accuracy that you need in order to describe the physical properties that you want to describe. So in order to get that, you have to consider which is the energy cutoff that you might need in order to get that. But in principle, you have to specify, in a practical way, you have to specify the energy cutoff you will consider in order to make the matrices, the dimension of the matrices finite. So the energy cutoff of the j vectors that you are going to include for each k are going to be those that satisfy that requirement, that the kinetic energy associated to them has to be lower than the energy cutoff you have considered for your numerical calculations. That's the typical way of truncating the matrices, the infinite dimension matrices that you do have for the CONSAM equations. And of course, once you have truncated that, you have finite matrices, and then considering that, you can calculate that the eigenvalues and the eigenvectors associated to each different k vectors in order to have the bands, the electronic band structure associated to this periodic solid.